In this video, we take a closer look at the keyed joint. The keyed joint generally belongs to the so-called shaft hub connections, and specifically to the positive locking connections. The keyed joint is used, for example, in gearboxes to connect gears with the gearbox shaft, and to transmit forces or torques. In the context of a shaft hub connection, the hub generally refers to the component that is to be connected to the shaft in a rotationally fixed manner. In our case, the gear is the hub, and the gearbox shaft is the shaft. Hubs can also be belt pulleys, coupling discs, flywheels, fan wheels, or brake discs. The force transmission between the shaft and the hub takes place through a driver called the key. The key, often made of quenched and tempered steel C45, is inserted into an axial groove milled into the shaft and protrudes a few millimeters above it. The groove in which the key is inserted is called the keyseat. The gear hub contains a corresponding axial slot, allowing the gear to be slid onto the shaft and the key. Torque can then be transmitted in a positive locking manner from the shaft through the key to the hub. Torque transmission is also possible in the opposite direction, meaning the gear can drive the shaft through the key. To prevent the gear from slipping off the shaft and to fix it in its axial position, certain securing elements are required. In our case, a so-called retaining ring is used, which is inserted into a radial groove in the shaft. For assembly and disassembly, the retaining ring is elastically expanded using special retaining ring pliers, also known as circlip pliers, and slipped onto or removed from the shaft. This highlights the major advantage of a keyed joint. Since it is a detachable connection, the components can be easily assembled and disassembled. Keyed joints are especially suitable when shafts or hubs need to be frequently maintained or replaced. Axial movability not only offers benefits during assembly and disassembly, but can also be intentionally desired, for example, when a hub must be axially movable during operation. This is the case with sliding couplings. This is referred to as a sliding fit, and the key is then called a sliding key or a floating key. Another advantage of the keyed joint is that the keys are standardized components and therefore relatively inexpensive. However, a disadvantage can be the reduction of the shaft cross-section caused by the machined grooves. In addition, the grooves in the hub and the shaft cause stress concentrations that lead to increased peak stresses. This weakening of the shaft and hub can increase the risk of failure under dynamic loads or high torques. In addition, unlike a cylindrical press fit, the keyed joint must be secured in the axial direction if axial movement is not desired, which increases the design effort due to the need for a retaining ring or a locknut. In addition, tolerances between the key, shaft, and hub can create a small clearance. Over time, under varying loads, this can lead to wear of the grooves. An exact positive drive of the hub by the shaft is then no longer possible. Furthermore, microscopic relative movement between the shaft and hub can cause so-called fretting corrosion over time, as the protective oxide layer that normally prevents further corrosion on the metal surface is constantly rubbed off and the surface corrodes again. This also leads to material weakening over time. In a keyed joint, different fits are distinguished depending on the tolerance grade combination of the key width and the groove width. While the key width has the tolerance grade H9, the groove width of both the hub and the shaft has the tolerance grade P9 in the case of a so-called tight fit of the key. This is a transition fit with slightly more interference than clearance. In this way, the key sits relatively firmly in the grooves. The diameters of the shaft and hub are also joined using a transition fit in this case, for example with the tolerance grade combination H7K6. In highly stressed keyed joints, especially under cyclic loading, such a tight fit is advantageous to prevent the key from loosening over time. However, the key and the hub cannot be assembled and disassembled as easily due to the tight fit. Despite the tight fit, alternative connection types should still be considered under variable loading conditions, as they may be better suited than a keyed joint in such cases, for example spline shaft connections. In a loose fit, also referred to as a transition fit, the keyseat width of the shaft has the tolerance grade N9, and the keyway width of the hub has the tolerance grade J9. This is also a transition fit, but with a larger maximum clearance and a smaller maximum interference. The diameter fit between shaft and hub is also designed as a transition fit with slightly more clearance than interference, for example H7J6. This overall results in easier assembly of the key and the hub, or the hub and the shaft. However, variable torque loading should be avoided due to the increased risk of loosening of the keyed joint. A sliding fit, also known as floating fit, is a clearance fit between the shaft and the key, as well as between the key and the hub. The keyseat width of the shaft has the tolerance grade H9, while the keyway width of the hub has the tolerance grade D10. The maximum and minimum clearance between the key and the hub is significantly greater than the maximum and minimum clearance between the key and the shaft. The shaft and hub diameters are also designed as clearance fits. This allows the hub to be easily slid axially over the key and the shaft. Variable loading of the key must be strictly avoided due to the greatly increased risk of loosening of the grooves. To reduce the previously mentioned risk of fretting corrosion, the key in a sliding fit should be secured with a fastening screw. For this purpose, there are special key profiles from type C to F. These have one or more holes for fastening a set screw. When using a key, it is generally important to avoid key lengths exceeding 1.3 times the shaft diameter due to excessive deformation of the key and the resulting uneven stress distribution. Additionally, the key length should be shorter than the hub length so that the key is fully enclosed within the hub and thus subjected to uniform stress. If, for example, a narrower gear is used whose width is smaller than the length of the key, a stepped hub must be used so that the hub length is increased and the entire length of the key is covered. Care should also be taken to ensure that the torque or force is transmitted as evenly as possible from the shaft over the entire length of the key to the hub. The hub design shown, for example, is not suitable for this purpose. If the load path is illustrated, it becomes clear that mainly the front part of the key is involved in transmitting the force. In the rear area, the torque is essentially already transmitted from the shaft via the gear. Therefore, hardly any force transmission takes place in this rear part of the key. As a result, the key, keyseat, and keyway are disproportionately loaded in the front area. With a stepped hub, the load path should therefore extend over the entire length of the key as much as possible. This can be achieved, for example, by moving the hub shoulder forward, thereby shifting the gear further toward the shaft end. It can then be seen that the load is transmitted over the entire length of the key, resulting in a more uniform stress distribution on the key seat, and the keyway. Let us now examine the design and strength verification of a keyed joint in more detail. For the design of keyed joints, the German standard DIN 6892 distinguishes a total of 3 methods. Method A is the most complex and deals with the strength verification of the shaft, the key, and the hub under real conditions, either through a realistic experiment or extensive numerical calculation methods such as the finite element method. The standard does not specify a concrete procedure for calculation method A. Calculation method B is somewhat less complex, and the calculation procedure is standardized. Method B specifically takes into account the surface pressure between the key and the keyway in the hub as well as the keyway in the shaft. This method is based on the assumption that the main failure criterion for the key joint is the allowable surface pressure between the shaft keyway and the key or between the key and the hub keyway. Nevertheless, with method B, the strength verification for the shaft must be carried out according to the nominal stress concept. Method B also considers impact loads, load direction changes, frequency of load peaks, friction factors, inhomogeneous load distribution along the key length, as well as support and hardness influence factors. Calculation method B is therefore still quite complex. That is why there is calculation method C for the preliminary design of keyed joints. This method is also based on the assumption that surface pressure is the critical failure criterion for the keyed joint. It simplifies the analysis by assuming a constant surface pressure over the entire length and height of the key. The usual fillets or chamfers at the edges of the keyways and keys are not taken into account. However, calculation method C can only be applied if the direction of the torque does not change. For a permanently alternating torque, calculation method B must be used. Even if the length of the key exceeds 1.3 times the shaft diameter, method C must not be applied because the shaft, key, and hub then deform too much and the surface pressure is no longer constant over the entire length of the key. In the following, we will examine the design of the key connection using method C in more detail. We assume that the shaft drives the gear with a torque M via the key. The shaft rotates clockwise. In this case, the left flank of the key seat exerts a force Fa on the left side surface of the key. The key, in turn, exerts a force Fb on the right flank of the keyway. The key seat surface marked in blue and the keyway surface marked in red, as well as the corresponding side surfaces of the key, are therefore primarily subjected to surface pressure. A shear load that attempts to shear off the key is also present, but if the key is selected according to standards, the shear load is significantly lower compared to the surface pressure. The permissible surface pressure is therefore the decisive factor and must not be exceeded, otherwise the shaft, hub, or key may be damaged at the corresponding contact surfaces. Since both the shaft and the key are very often made of high-strength materials such as tempered steels due to the high load, the hub material is usually the one with the lower load capacity. Therefore, the hub material often has the lowest permissible surface pressure, which means that the design of the key connection is mainly based on the hub material as the weakest component. In the following, the surface pressure between the key and the hub is determined for a given shaft diameter d and a given shaft torque m. The surface pressure P generally describes the force distribution on the contact surface of the two components and is calculated as the quotient of the force F acting on the hub and the contact surface A, marked in red, between the key and the hub. For simplification, it is assumed that both forces act at the circumference of the shaft and are therefore equal in magnitude. This means that the force F exerted by the shaft on the key is equal to the force with which the key presses against the hub. In this way, the acting force F can be easily calculated from the torque M of the shaft and the shaft diameter d. The torque M is defined as the product of the force F and the lever arm R, which is perpendicular to the force. In this case, the lever arm corresponds to the radius of the shaft and is therefore equal to half the shaft diameter. Thus, the torque is calculated as the product of the force and half the shaft diameter. By rearranging this equation, the resulting contact force between the key and the hub can be determined for a given torque M and shaft diameter d. The formula shows that the resulting contact force on the hub increases as the distance between the force and the center point decreases. Since we have assumed that the hub force acts closer to the center point, this formula yields a slightly higher force than actually occurs in reality. As a result, we automatically obtain a kind of safety factor by assuming a greater force than is actually acting. To determine the contact pressure, we need the rectangular contact area between the key and the hub, which is the product of the load-bearing height ht and the load-bearing length lt. We assume that the shaft has a keyseat depth t1 and the hub has a corresponding keyway depth t2. The specified depths always refer to the shaft diameter or the bore diameter of the hub. Depending on the shaft diameter, both depths are standardized. We will explain this in more detail later. The keyseat is generally deeper than the keyway, so the key with height h sits deeper in the shaft than in the hub. The height of the key is always smaller than the sum of the groove depths, so the key always has a certain clearance. The key height is also standardized depending on the shaft diameter. For the red-marked contact area, the relevant portion of the key height is the part that protrudes from the shaft and presses the key against the hub. Since the key with its height h sits in the shaft to a depth of t1, the portion of the key protruding from the shaft corresponds to the difference between the key height h and the keyseat depth t1. This is referred to as the load-bearing height ht. Due to the curvature of the shaft and the width of the keyseat, however, this calculation results in a slightly smaller contact height than is actually present. Therefore, the red-marked height of the contact area is somewhat reduced by this consideration. This is not critical, as it results in a smaller contact area than actually present, leading us to assume a higher contact pressure than what occurs in reality. Thus, we automatically obtain a kind of safety factor again. Now we still need the load-bearing length Lt of the contact area between the key and the keyway. It should be noted that not the entire length L of the key with rounded ends contacts the keyway wall. Unlike the shaft, where the key also contacts the keyseat with its rounded ends, the hub features a straight continuous keyway. Therefore, the key only contacts the hub keyway wall along its straight section. To determine the load-bearing length Lt for rounded end keys, twice the radius of the rounded end must be subtracted from the total key length L. Twice the radius corresponds exactly to the diameter of the rounding. The diameter, in turn, is equal to the width b of the key. Therefore, to determine the load-bearing length Lt, the key width b must be subtracted from the key length L. However, it should be noted that this only applies to rounded end keys. For square end keys, the load-bearing length is equal to the total length of the key. In this case, the width b of the key is mathematically set to 0 in the formula. This does not mean that square end keys have no width. It is simply a mathematical simplification, since no rounding needs to be considered in the formula. We can now determine the contact area A as the product of the load-bearing length Lt and the load-bearing height ht, as specified. Using this expression in the formula for calculating the contact pressure, and expressing the force with the previously derived term, we obtain the given formula for calculating the contact pressure between the key and the hub. This acting contact pressure must not exceed a certain maximum allowable contact pressure P allow, depending on the hub material. Therefore, the condition applies that the acting contact pressure must always be less than, or in the limiting case equal to the maximum allowable contact pressure PALL. Since the key seat depth T1 and the key height H are specified depending on the shaft diameter, the load-bearing length LT of the key must be chosen so that the resulting contact pressure does not exceed the allowable contact pressure. To do this, we solve the equation under the condition that the acting contact pressure, in the limiting case, equals the maximum allowable contact pressure for the required load-bearing length. This gives us the minimum required load-bearing length of the key. Since the key width is also standardized depending on the shaft diameter, we can thus determine the required total key length and select the corresponding key. For this purpose, we rearrange the formula for the load-bearing length to solve for the required key length L. Let's consider an example. To secure a pulley, a key connection is to be used. For the axial securing of the pulley, a slotted locknut with a tab washer is employed this time. First, let's take a closer look at the assembly of this connection, which presents an alternative method of axial fixation of the hub compared to the previously used retaining ring. During assembly, the key is first inserted, and then the pulley is pushed onto the shaft shoulder. A washer serves as a bearing surface to better distribute the force when tightening the locknut. For this purpose, the front part of the shaft is threaded. Before screwing on the slotted locknut, however, a tab washer is slid over the thread. The tab washer has an odd number of locking tabs on its outer diameter, and an additional tab on its inner diameter. A corresponding groove is milled into the thread itself, into which the inner tab engages when the washer is slid onto the thread. This prevents the tab washer from rotating during operation. Next, the slotted locknut is screwed on. It has 4 slots around its circumference. We can now see that due to the odd number of locking tabs, their positions relative to the slots differ slightly. This ensures that one of the tabs fits into one of the 4 slots without the locknut having to be excessively rotated. The corresponding tab is then bent over and engages positively in the slot of the nut. In this way, the nut cannot loosen by itself during operation, as the tab washer is positively secured against rotation by engaging with the slot in the thread. Let us now turn to the actual key joint and the corresponding selection of the suitable key. The relevant shaft diameter for the key connection is 40 mm. A torque of 240 Nm is to be transmitted to the pulley via this shaft. The allowable contact pressure of the hub is 200 newtons per square millimeter. The key to be used is of type A, which is the well-known rounded end version without holes for retaining screws. The geometry of the key and the seating depth essentially depend on the shaft diameter and are standardized accordingly. Detailed information can be found in the engineering handbook. In our case, with a diameter of 40 mm, we refer to the column for the nominal size range between 38 and 44 mm. There, among other data, we find the specified key width of B equals 12 mm, the key height of H equals 8 mm, the shaft keyseat depth T1 equals 5 mm, and the hub keyway depth T2 equals 3.3 mm. The only dimension we can influence is the key length L, which must now be chosen so that the allowable contact pressure is not exceeded. We can determine this using the derived formulas. For this, we first need the load-bearing height HT. We calculate this as the difference between the key height H and the key seat depth T1. Using the values, we obtain a load-bearing height of 3 mm. With this load-bearing height, we can now determine the required load-bearing length LT of the key. When using the values, attention must be paid to the units. Since the diameter D and the load-bearing height HT are given in millimeters, and the allowable contact pressure is given in newtons per square millimeter, the torque must also be expressed in newton millimeters. To do this, we multiply the torque of 240 newton meters by a factor of 1,000, resulting in a torque of 240,000 newton millimeters. This ensures that the resulting load-bearing length is also obtained in millimeters. In our case, we get a required load-bearing length of 20 millimeters. Next, the total length L of the key must be determined, since for the standardized specification the total length, not the load-bearing length, is relevant. For Form A, we must consider the rounding of the end faces and therefore add the key width to the load-bearing length as specified. With a width of 12 mm, this results in a total key length of L equals 32 mm. It should be noted that keys are not available in arbitrary lengths, but rather in specific increments. If a calculated key length is not exactly available, the next larger length must generally be chosen. The standard compliant specification of a key according to the German DIN standard includes, after the corresponding DIN designation, the shape of the key, the width, the height, and the length. As already explained, the key length should not exceed 1.3 times the shaft diameter in order to avoid excessive deformations and thus uneven stresses. However, if this is the case, 2 keys offset by 180 degrees can be used. More than 2 keys are not permitted. In such cases, other types of connections, such as the spline connection mentioned earlier, must be used. When using 2 keys, it must be noted that both cannot be perfectly aligned. Therefore, the keys are usually subjected to uneven loads. Due to this asymmetric load distribution, using 2 keys does not mean that the connection can withstand twice the load. To take this into account, there is a so-called load factor. A load factor of, for example, phi equals 0.75 means that the load is not evenly distributed on one key, but only to 75%. Both keys together can then withstand not the double load, but only 1.5 times the load. The formula for the surface pressure can therefore be extended as shown. In this formula, N represents the number of keys and phi the load factor. For the use of only one key, N equals 1 and the load factor phi is also 1. When using 2 keys, N equals 2 and the load factor phi is 0.75. The formula for determining the required load-bearing length of a key must also be adjusted accordingly. This results in the calculation formula as stated. When using 2 keys, it may sometimes be better not to use high-strength keys, but rather keys made of a somewhat softer material. Under load, deformation processes cause the keys to deform slightly and conform better to the respective grooves, resulting in a more uniform distribution of force.